Welcome! In the previous video, we talked about a few problems with the coefficient of variation. One of those problems is that the coefficient of variation is theoretically unbounded. In other words, it can become very large, especially when the average value is close to zero. In statistics, it is often useful to work with quantities that are bounded between 0 and 1. For that purpose, we can use the second order coefficient of variation, V2, which is defined as the square root of the variance divided by the squared average plus the variance, which is equal to the standard deviation divided by the square root of the squared average plus the variance. So how can we interpret this coefficient? Well, if the standard deviation is large and the average value is small, then the variance dominates the denominator. In that case, the second order coefficient of variation tends toward 1. This means that the data has high relative variation. On the other hand, if the standard deviation is small and the average value is large, then the squared average dominates the denominator. In that case, the coefficient tends towards 0. This means that the data has low relative variation. Now let's look at a few special cases. If the standard deviation is 0, then there is no variation in the data. In that case, the second order coefficient of variation is 0. If both the standard deviation and the average are 0, then the formula gives us 0 divided by 0, which is mathematically undefined. However, in practical applications, we may choose to define this coefficient as 0 in this case, because the data has no variation. Also, if the average is 0 and the standard deviation is greater than 0, then the second order coefficient of variation is equal to 1, regardless of the actual value of the standard deviation. One more interesting property of the second order coefficient of variation is that it can be expressed as a function of the ordinary coefficient of variation. Dividing the numerator and the denominator with squared average gives us the square root of the squared coefficient of variation divided by 1 plus the squared coefficient of variation. This is useful because we can plot the second order coefficient of variation with respect to the ordinary coefficient of variation. The graph looks something like this. As the ordinary coefficient of variation increases, the second order coefficient also increases. That makes it a useful bounded alternative for describing relative variability in data. However, it is important to mention that the second order coefficient of variation is not location invariant. That means that adding a constant offset to all data points can change its value. If you are not sure what location invariance means, please check out my previous video. On the other hand, the second order coefficient of variation is scale invariant. This means that changing the measurement unit by multiplying all data values by a constant does not change the coefficient. The same is true for the ordinary coefficient of variation. So to summarize, the second order coefficient of variation is a bounded measure of relative variability. It can be used as an alternative for the ordinary coefficient of variation. That's it for this video. I hope you enjoyed it and good luck with your work.